transforms, and in our next session, probably we'll learn the last of the topics. Is going to be how to solve differential equations using Laplace equations, Laplace transforms. That is going to be our main topic. So let me start with that. So basically, we want to learn how to solve differential equations, easy ones, using Laplace transform. In your syllabus, there are easy differential equations, so I'll only restrict to those kind of differential equations. Basically, second order or first order linear differential equations with constant coefficients is what we solve. But with initial, there will be initial value problem, which means you should know the value of the solution at some initial point, 0 or whatever, I or the problem. Basically, it will be a IVP, initial value problem. So to do this, I want to relate Laplace transform of a function with its derivative. Let's just try to, I can't say understand because we're not writing the proofs of anything. Let me tell you the formula which relates Laplace transform of a function with Laplace transform of its derivative. So this is the formula. L of ft is, if L of ft is capital F of x, this is our usual notation, then Laplace of its derivative is given by s times Laplace of f minus f0. That means whatever this function value at 0 is, you have to subtract from s into Laplace of ft to get Laplace of f dash t, that is derivative. So this is the formula. It's not difficult. It's very easy to prove this. Basically, you need to know some differentiation and integral sign or some such thing. You write down the definitions and you will get it. It's not difficult, but it's not there in your syllabus, so I am not going to write the proof of it. But you need to remember this. L of f dash t is s times LFT minus f0. So what we have done is we have written. So what you need to understand is we have written Laplace of derivative in terms of Laplace of the function itself. That is what we have done. There isn't really, means I can't really see a good problem to illustrate this result. So I will take one of the standard ones which says, deduce L of cos t from L sin t. Of course, we know already what is Laplace of cos t, Laplace of sin t, both we know. But just to illustrate this formula, I will take up this question. So we know in this question it's asked to deduce L of cos t from L sin t. So that means we know L of sin t. So L of sin t we know as 1 by s square plus a square. From this, try to deduce L of cos, Laplace of cos. So I know cos is derivative of sine. So L of cos t is SL. So if you take ft equal to cos t in this formula, if you take ft equal to cos t, then L of cos t I know is s by s square. From sine t. So you take ft to be sine t. So if you take ft to be sine t, then capital F of s is 1 by s square plus a square. L of ft is sine t. So L of f dash t, which f dash t is cos t. So L of cos t is s times L of ft. That is 1 by s square plus a square. So s into 1 by s square plus a square is s by s square plus a square, which we know it from beginning. Minus f of 0. This formula says f of 0. F is sine, so sine 0 is 0. So this term will be 0. Similarly, one can ask equally named question which says deduce L sin t from L cos t. So if you want to deduce that, then you take ft equal to cos t and then carry out, then you get cos 0 is 1 and you make some minor fractional manipulation. You will get one from the other. This is just to make you understand this formula, that L of f dash t in terms of LFT is what I have written. So just to make you understand that, you have to go through this illustration. More importantly, where I will use that is in solving differential equations. That is what I am trying to illustrate. I want to make you understand. So in fact, you use this same formula L of f dash t equal to S LFT minus F0 twice. That means I want to find LF double dash T in terms of LFT. So first I will take here F itself to be F dash. In this formula, what you saw here, we take F to be F dash. So then L of F dash dash T, that means F double dash T, is SLFT minus F dash 0. Replace F by F dash, you will get this formula. L of F double dash T is S times L F dash minus F dash 0. But I know L of F dash in terms of L of F. For that I use the same formula once more. So this is S L of F dash is SLF minus F0, and this minus F dash 0 I return it as it is. You expand this, you will get S square LF minus SF0 minus F dash 0. Just expanding this, opening this bracket, that's all. So you use the same formula twice to get Laplace of the second derivative of F. If I know Laplace of F, I know Laplace of second derivative of F. Nothing special about second derivative. I can also find about third derivative. If you just use this once more, I'm sure you'll get S cube minus LF minus S square times F0 minus S F dash 0 minus F double dash 0. Is a, you know, you can keep defining it inductively or recursively, whatever you want to call it. So inductively, I think you can find Laplace of derivative of any order of the function. If I know Laplace of the function, I'll know Laplace of derivative of any order. So I'm going to just write it as a formula. We never use this. We will use at the most till 3, but just you should know that there exists such formula. L of nth derivative of f is s power n lft minus s power n minus 1 f0 minus sn minus 2 f dash 0, etc., up to n minus 1th derivative of f at 0. Please note here I'm slightly sort of cheating. If you just know L of, for example, let us take the first one only. If you just know L of ft, you don't know L of f dash t. You must also know f0. You must know f. You know f, then you know f0. Then you know, if you know L of f0, L of ft, then you know s into L of ft minus f0. So this is what this formula is all about. So if you want to know nth Laplace of nth derivative of f, then you need to know not only Laplace of f, you also need to know what is value of f at 0, f dash at 0, f double dash at 0, etc. up to n minus 1th derivative of f at 0. That much you need to know. So if you give me expression for f, then I'll be able to compute all these things. So we won't use these kind of formula in this sense. So I will not even give you illustration of these things. But I will use this formula to solve linear differential equations with constant coefficients. So I'll show you an illustration. Basically, yeah, this is what I want to show you. I want to tell you that I will give you solution of linear differential equations with constant coefficients. Basically, IVP. IVP means initial value problem. Why is it called initial value problem? Because I need to know these values f0, f dash 0, f triple dash 0, f double dash 0, depending on the order of the differential equation. I need to know this. Only then I know what is L f dash. If I know f0, only then I know what is L of f dash. Otherwise, I won't know. So such problems, as you might have studied, is called initial value problem. The advantages is that these are very short methods. That was the purpose of Laplace. In fact, I'm tempted to digress a bit and tell you something about history of this Laplace transform. It was not Laplace who found this Laplace transform. Laplace was the one who popularized this. The one who found this this idea of solving, idea of this so-called Laplace transform as a tool to solve differential equations first came from Euler. Uh, so Euler did this first, but Laplace popularized this and sort of used that technique to solve many differential equations. In fact, Laplace was so egoistic, and so he never credited it to Euler. His book, I forget the name. The book title. It seems Laplace would write books where he would never sort of tell where he got his ideas from. Means it's not the original ideas never acknowledged. Doesn't claim it's all his work, but he doesn't tell where it has come from. He just writes it as if he's the final word on it. So a lot of people think this is Laplace transform. Actually, it should have been called Euler transform. But anyway, Euler has enough things to use, so it doesn't matter. So anyway, that was just a masala. We will find general solutions and then evaluate the constants. I mean, this is what we do normally. If you are asked to solve this IVP, normally you would find general solution of a differential equation and then find what is those constant. Like whenever you find the differential equation, you get y is equal to f of x plus c. Some constant would come. How do you evaluate that constant using these initial conditions? So all those things you don't have to do in this method. So before I tell the method, I want to emphasize on the idea. I want to emphasize on the formula. This is the basic formula. L of f dash t is S of f0 minus f of 0. L of small f prime t, that is L of derivative of ft, is S times Laplace of f, that is capital Fs, minus value of small f at 0. This is the formula. I have not proved this. Just accept that. And using it twice, you will get LF double dash t is S square Fs minus SF0 minus f dash 0. And use it thrice, 4 times, depending on what is the order of your differential equation. You will get these kind of results. Oh, there is a small mistake here. This is not equal to, but this is minus. Slightly. So this is what L triple dash is. I'll not use this also. I will in my class in illustration I'll use only these two. But you should know there exist such things. And some notation. Again, you see L of y. Till now I had not used y. I had been using f. L of small f is capital F. Capital F of S. Now I will even drop that S. I will just say capital F. L of small f is capital F. L of small y is capital Y. Basically, we drop that S. And it's not, we understand that capital Y is a function of S. So we won't emphasize on that S there. So this is the notation. L of Y is capital Y. So in this notation, L of Y, which is capital Y, sorry, L of Y dash is S capital Y minus Y0. Capital Y means L of Y. Just notation, that's all. If more I say, more you will get confused. L of Y double dash is S square Y. I will not write this S in the problem. Just to highlight that this capital Y is a function of S, I have written it here. SY0 minus Y dash 0. Similarly, Laplace of third derivative of Y is whatever you see on your screen. So let us try to, with this much of preface, let's try to get into how to solve these differential equations. So let us spend a few minutes on trying to understand what does one mean by solving differential equation. You see, here is a differential equation, dy by dt plus y equal to sine t, and solve this. Given that y0 is 0, what does this mean? Okay, I know all of you have, most of you have already understood this. You know how to solve this differential equation, but I somehow feel I need to tell you a few words about what do you mean by solution of, what do you mean by solve this differential equation dy by dt plus y equal to sine t. What it means is you find, okay, I'll give you another example. I have not made slides for that, but I'll give you examples. Solve x plus 2 equal to 5. What does it mean? Just forget about this Laplace transform business now. First time when you heard solve, so you heard something, some equation like this. Solve x plus 2 equal to 5. What does that mean? It means find a number x such that if you add 2 to it, the result answer must be 5. So same thing said in different words is, I have this equation x plus 2 equal to 5. You find a solve that means you find a number x such that x plus 2 equal to 5 is true. It will become correct. So answer of course is 3. X equal to 3 is the only number which will make x plus 2 equal to 5 as a correct statement. Others, if you put x equal to anything else, x plus 2 equal to 5 is not a correct statement. It's a wrong statement. For example, you put x equal to 10, 10 plus 2 is not equal to 5. You put x equal to 1, 1 plus 2 is not equal to 5. If you put x equal to 3, 3 plus 2 is 5, it will make that statement as true statement. So solving the equation x plus 2 equal to 5 means find a number such that if I substitute that number into this equation is true. Same philosophy holds good here also. Here what one is asking is solve this means find a function y of t such that if I substitute that y of t in this equation must be true. Let's see, just for sake of it. Let us take y equal to sine t. It's a function. Sure. Y equal to sine t. If I substitute in this, dy by dt is dy is sine t, so dy by dt is cos t. Cos t plus sine t is equal to sine t. Is that correct? No, it is not true. So y equal to sine t is not a solution of this differential equation. So what is the solution of differential equation? That's the question. We have to find it. Of course, there may be many functions. All will be varying, because how will you solve this dy by dt? For example, just assume you have just dy by dt equal to sine t. Assume that y is not there. Just even simpler, dy by dt equal to sine t. Solve that means what? Solve that means find a function such that when you differentiate with respect to t, answer is going to be sine. That I know is minus cos is the answer. How did I get that? Separating variables, integrate. Basically, integration is what we are doing here to solve this kind of differential equations. But that is calculus. So we want to avoid calculus. As I said, Laplace transform is a way of solving differential equations without using calculus, only algebraic. I want to convert this into algebraic equation. You have done such things before. You saw d by dt as capital D, and you can rewrite this as d plus 1 times y equal to sine t. You know how to solve such things. You learned in your first semester. I'm going to tell you a similar method, not the same method, a similar method where it's going to be only algebraic equation. Like there also you saw, no, in that method, if you can recall, you solve this. How do you solve this? You would rewrite it as capital D plus 1 times y equal to sine t, and then find complementary function, which means d plus m plus 1 equal to 0. Root of that is minus 1. So minus 1 is the only root. So general solution is a into e to the power of minus x, correct? So here t. So a into e power minus t plus some particular integral. How do you find particular integral? So you will have to write 1 by d plus 1 sine t, and then something you did all sorts of things to solve that. So they were all algebraic way. There was no calculus there. Very little calculus was there finally. I want to do a similar method, but not so with so many so much of paraphernalia. So I'll try to do it in a shorter way. So how to solve this? So let me emphasize again. Solve this means find a function which, when I substitute that function into this equation, this equation becomes true, and that function, in addition to satisfying this equation, must also have the property that y of 0 is 0. That's why it's called initial value problem, which means initially when x equal to 0, y is 0. That's what defines the function. And of course, the function must satisfy this. How to solve this? So I'll rewrite this equation as y prime plus y equal to sine t. Note, independent variable can be t or x or anything. In this problem, independent variable is t and dependent variable is y. Sometimes dependent variable will be x and independent variable will be t, or sometimes dependent variable will be y and independent variable will be x. That's the case you must have seen most often. So you have to figure out in the problem which is the independent variable, which is the dependent variable. So this means, let me reiterate this. Y of 0 is 0 means y at t equal to 0 is 0. That's what this means. So I want to find the solution of this differential equation. All this you knew before, and I'm just trying to recall. Now I will tell you how do I use Laplace transform to solve this differential equation. First, take Laplace of this equation. This is the given equation. Given ordinary differential equation is dy by dt plus y equal to sine t. Take Laplace. That means y dash plus y equal to sine t. That's how I write this, no? Y dash plus y equal to sine t. Now y dash plus y equal to sine t, take Laplace of this full equation. That means left hand side you will have Laplace of y dash plus y, and on the right hand side you will have Laplace of sine t. I hope it's clear. I'm just taking Laplace of this differential equation. Now I will use properties of Laplace transform which I have studied all these days. So Laplace is linear operator, so L of y dash plus y is same as Laplace of y dash plus Laplace of y. And Laplace of sine t is 1 by s square plus 1. I know it by using standard table of Laplace transforms. Now I want to basically want to find small y, remember that. So procedure is L of y dash plus L of y equal to 1 by s square plus 1. Now I know L of y dash in terms of L of y. I know, I just told you one formula. It said it is s times Laplace of y minus value of y at 0. So I written it as s of capital Y minus y of 0 plus L of y itself is capital Y. Here also there is a L of y because L of y dash is s times L of y minus y of 0. So that's what I have written here. So I substituted for L of y dash. I substituted s capital Y minus small y 0, and Ly is capital Y. That's the notation equal to s square plus 1. Now you saw y of 0. Do I know? Yes, I know y of 0 is 0. So this term is gone. I don't bother with it. Remaining thing is s into y plus y is 1 by s square plus 1. Remember, I'm trying to find small y. So first let me find what is capital Y. So solve this equation for capital Y. That means make y as the what is called subject of the formula. So then you will get s. So I'm simplifying it here. S plus 1 times y equal to 1 by s square plus 1, which means capital Y is 1 by s plus 1 into 1 by s 1 by s plus 1 into s square plus 1. Have I solved the problem? Not really. I just found what I have found is capital Y. What is capital Y? It is Laplace of small y. I am asked to find small y. What I have found is capital Y. So I want to go from capital Y to small y. How do I go? I will take inverse Laplace. That's all. If I take inverse Laplace of capital Y, I'll get small y. So now I should know how to take inverse. So ideally I should have written it this as capital Y of s. It's a function of s. But I won't write it. It's understood that. That's understood. So capital Y is equal to 1 by s plus 1 into s square plus 1. Take inverse Laplace of this. I'll get small y, which is inverse Laplace of capital Y, is inverse Laplace of 1 by s plus 1 into 1 by s square plus 1. Do I know how to find inverse Laplace of 1 by s plus 1 and into 1 by s square plus 1? There are several ways of dealing with this problem. This, easiest thing is to write partial fractions. This is I'm not written on all these details, but since I have already done that in the previous lecture, I will just very briefly recall. This is a rational algebraic expression, and I have numerator 1 and denominator has two terms, s plus 1 and s square plus 1. Both are irreducible, meaning I can't factorize this further. S square plus 1 I can factorize with real numbers, and s plus 1 is anyway degree 1. So I will rewrite this as partial fractions a by s plus 1 plus bs plus c by s square plus 1, because it's a quadratic term. Numerator can have, the worst case, a linear term. So it must be bs plus c. So remember, this I'll have to write it as a by s plus 1 plus bs plus c divided by s square plus 1. And then use your partial fractions knowledge to find out the values of a, b and c. Maybe you will put s equal to -1 and then correct the portions of s square, equate on both sides, equate constant portions and things like that. You can find a, b, c. I have not written down those details here, but I'm sure I have done this when I taught you how to find inverse Laplace transform using partial fractions. So this is basically 1 by 2. So a will turn out, if you write this as a by s plus 1 plus bs plus c by s square plus 1, a will turn out to be half, b will turn out to be minus half, and c will turn out to be half. So if I substitute all that in this, I'll get the small y is Laplace inverse of this, which is same as half times Laplace inverse of, actually it will be Laplace inverse of half s plus 1 minus half s by s square plus 1 plus half 1 by s square plus 1. This half I can take it out because Laplace inverse is also a linear operator. So I'm left with L inverse of 1 by s plus 1 minus 1 by s square plus 1 plus 1 by s square plus 1. So, but each of these terms, it's very easy to find inverse Laplace. What is the inverse Laplace of 1 by s plus 1? Correct, e power minus t. What is the Laplace transform of s by s square plus 1? Sin t, correct. And sorry, cos t. And this is sin t. So I write down all these things. So since I know how to find inverse Laplace, I do this. So this small y is equal to half e power minus t minus cos t plus sin t. I get this by taking inverse Laplace. I should have written one more step extra because L inverse is linear. I can write this as half L inverse of 1 by s plus 1 minus half L inverse of s by s square plus 1 plus half L inverse of 1 by s square plus 1. So each of the L inverse of s plus 1, L inverse of s by s square plus 1, etc. I have written it down here. So this is the solution. Over. You solve the problem because I have found y as a function of t. This is what it is. Now, so we didn't do any calculus at all anywhere. We didn't integrate, we didn't differentiate, nothing we did. All we did was to use this formula. Ly dash is s of y minus y of 0 and solve for capital Y, which is inverse Laplace of y, sorry, Laplace of y. And then to find y itself, we took inverse Laplace. Again, it had no calculus in it, just partial fractions. And we obtained the solution. So we have obtained the solution of differential equation with no differentiation or no integration. Purely algebraic methods means it is symbolic manipulation and then used partial fraction theory. Of course, I'm hiding all the integration. That was the idea of Euler. What we are doing essentially here is, you see, in this step, when you take Laplace of this, means what? Means you multiply, like what do you remember, recall what is the definition of L of sin t? L of sin t is integral of e power minus st sin t as t varies from 0 to infinity. So you're basically multiplying this equation by e power minus st and then integrating. That's what we are doing. You can't integrate this directly because if you integrate this equation directly, you will get integral of dy, I mean multiply by dt and then integrate. So integral of dy will be y, but integral of y dt I don't know. I don't know y as a function of t. That's the problem. I have to try to find it. Integral of sin t dt I know. So I don't know what is integral of sin t. So it doesn't work like that. You can't directly integrate. So you have some method where, oh, if the equation is given some particular form, we can always multiply by an integrating factor and then integrate. Then the integration becomes easy. So what Euler told is, you always multiply by e power minus st. Integration will become easy. That's what he had to tell. So that he converted this into symbols like using capital L. Not Euler, Laplace did that. That's why he's famous. So it's like e power minus st is sort of universal integrating factor and integrated between t equal to 0 to infinity. That's what we have done here. That was the idea of Euler, which Laplace sort of appropriated. So this is L of y dash plus y means you multiply this by e power minus st and integrate. Instead of keep on telling multiply by e power minus st and integrate between t equal to 0 to infinity, I'll say take Laplace of it. Both are same because that's the definition of taking Laplace. And then I use properties of Laplace, which to prove those things which we did not do it in this course. You need to do a lot of integration and differentiation. So all the hard work of integration and differentiation is hidden in those proofs. But you don't have to bother about that. You just do the symbolic manipulation. So that is what. So this gave us the solution. How do I know this is a solution? Recall. What do you mean by this is a solution? It means if I substitute this function in the original differential equation, I should get, it should make this original differential equation as true. And also y of 0 must be 0. First let's check that. Why is y of 0 0? So let us check that. Oops, sorry. How do I check? If you put p equal to 0, what do I get? E power 0 is 1. Cos 0 is what? 1. And sine 0 is 0. So 1 minus this e power 0 is 1, cos 0 is also 1. So 1 minus 1 is 0 plus 0 is 0. So y of 0 at t equal to 0, this term becomes 0. So this does indeed satisfy one of the conditions given. Does it satisfy the other condition? What are the other condition? Other condition is dy by dt plus y must be equal to sin t. That means if you differentiate this function once, if you differentiate this function once and add it to this function itself, answer must be sin t. Does it happen like that? It's very easy. Check it. How do I check? Just find out the derivative of this. No? That's what you have to do. So, indeed, to check that this is a solution, all I have to find is y dash t. That's very easily done term wise. Half is anyway constant outside. Derivative of e power minus t is minus e power minus t. Derivative of minus cos t is plus sin t. Derivative of sin t is cos t. Now you add these two. If I add these two will get half and take it out. E power minus t and minus e power minus t get cancelled. Sin t and sin t get cancelled. What I'll be left with, I'm adding these two, minus cos t and cos t will get cancelled. Sin t plus sin t will become 2 sin t, but there is a half outside, so half 2 sin t will be sin t. So indeed, right hand side, if I add these two, I will get sin t. That's what I wanted. This function, I wanted it to satisfy my differential equation. Here I proved that it satisfies the differential equation. Don't worry, whatever you see in this slide, you are not expected to do in the exam, but it's easy to verify. You will know whether you have done it correct or not. You have to just substitute this value of y into the given differential equation. That's all you have to do. I won't keep doing it every time, but I just wanted to make sure you understand what does it mean to say solution of a differential equation. So I explained this in great detail. I will not do this for every problem, but I expect you to do at least for a few of them. In the exam, you are not expected to do this checking of the solution. But in general, it's a good habit to keep checking your solution is right or wrong. Does it satisfy all the property which is given or not? These kind of things will help you make sure that you don't do it wrong. So here is another example. The first equation, before I go to second equation, I have some more stories to tell. So first equation, remember, this is dy by dt plus y equal to sin t. This is linear differential equation of degree 1, order 1. This is dy by dt is there. It is not d square y by dt. So order is 1. Of course, degree is also 1 because its power is 1. Degree is not very important for me right now. The order is 1. So I needed only one condition. Y0 is 0. One condition is sufficient to tell me what was to find out the solution for this differential equation. Now in the second problem, in this problem, you see this is a second order linear differential equation. It's a second order because the highest derivative is d square y by dx square. And this is linear, of course, because you have differential equations. Not all. This differential equation is linear, and coefficients are constant. So this is a linear differential equation of order 2. D square y by dx square minus 2 times dy by dx plus y equal to e power x. I want to solve this. That means what? I want to find a function which, when I substitute in this, it becomes true. What becomes true? This equation becomes true. I mean, I'm on the lookout for a function which when you differentiate twice with respect to x, of course, because of how function. So, that's another thing you have to figure out initially. The moment you see the function, the problem. Independent variable is x and dependent variable is y. D square y by dx square or dy by dx means it tells you that y is dependent on x. Y is a function of x, which is what you are trying to find. So I want to find such a function of x, y of x, such that its second derivative minus twice the first derivative plus the function turns out to be e power x. Very complicated question if somebody asks like that. But mathematicians have made it very simple by just saying solve. There's one word, it has hidden so many things. It's telling you find a function y of x such that second derivative of that function minus twice the first derivative of the function plus the function itself gives you e power x. Such a long sentence, it just says solve. Yes. Now also in addition to that, I want y of x to be satisfying these initial conditions. That means At x equal to 0, y must be 2 and dy by dx must be minus 1. That means y of 0 is 2 and y of 0 is minus, y dash of 0 is minus 1. Remember, dy by dx means y dash. So this, please try to understand this statement. When x equal to 0, y equal to 2 and dy by dx equal to minus 1. The value of this is not just y equal to 2. This means actually, ideally it should have been written y of 0 is 2. Y when x is 0 must be 2. That's what one means by writing this. When x equal to 0, y equal to 2. And dy by dx is minus 1 at x equal to 0. That means y dash at 0 is minus 1. Y at 0 is 2. So these are two conditions. Y of 0 is 2 and y dash 0 is minus 1 are two conditions. I need two conditions if I want to solve differential equation of second order. Differential equation of first order, I can solve with one condition. One condition is all I require. But differential equation of second order, I need two conditions. If it were a differential equation of third order, that means, for example, if it were there d cube y by dx cube plus etc. 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 then I would have needed three conditions. I would have needed at x equal to 0, y equal to 2, dy by dx equal to minus 1, and d square y by dx square equal to what also I needed to know at x equal to 0. Otherwise, I won't be able to solve the problem using Laplace transforms. So now trick is the same thing. Start with differential equation. Take Laplace of this ODE. So this, what is this ODE? Let's write it in the form in which is easy to take Laplace transform and write its formula. So I'll write this as y double dash minus 2y dash plus y equal to e power x. There's no t here, so don't get confused. This is the kind of things which examiners play on, so you have to be careful about it. There's no t here, there's only x. So this differential equation is y double dash minus 2y dash plus y equal to e power x. And now I'll take Laplace of this. That means I'll get Laplace of y double dash minus 2y dash plus y equal to Laplace of e power x. So you take up, so now because it is linear, I can break up. So it will be L y double prime minus 2 ly prime plus ly equal to L e power x. This I know how to write it all. I know ly double dash how to write in terms of ly. I know ly dash how to write in terms of ly. This is ly itself. I know L e power x. So I know I can solve for ly double prime, ly, that is capital Y. I can find it. So let me, instead of telling you, show you this. So I use this formula. Ly double dash is s square capital Y minus sy0 minus y dash 0. This is the formula. How does Laplace of second, if knowing Laplace of first derivative, how to find Laplace of, knowing Laplace of a function, how to find Laplace of its second derivative. That formula is what I have used here. And here I have used the other formula. It says if I know Laplace of small y, which is capital Y here, I know Laplace of y dash. What is the formula? Sy minus small y is here. So that's what this formula is. So I substitute that here, and Ly I have written as it is. So Laplace of e power x I know is 1 by x minus 1. Don't ask me why, sir, there is t here. It's the same thing, it doesn't matter. You can call it with whatever variable. Here instead of t, this problem uses x, that's all. So this is using this formula, L of y double dash minus 2 ly dash plus ly equal to L e power x. I substitute Ly double dash is s square y minus sy0 minus y dash 0, and this Ly dash is sy minus y0. Capital Y I write it like that, and L of e power x is 1 by x minus 1. Now solve for capital Y. But then I need to know y0 and y dash 0. Yeah, I know that. That is precisely what the initial value problem is all about. They have given me y at 0 is 2 and y dash at 0 is minus 2. That is what is data is given to me. So unless you give me these things, I cannot proceed. So Laplace transforms, using Laplace transform, you can solve initial value problems. You can't solve all differential equations, but that's okay. Initial value problem is a very large class of problems. So if I know y of 0, I know y of 0 is 2 and y dash 0 is minus 1. So I substitute all that here to get s square y, I'll write as it is, y0 is 2, so I'll get minus 2s, and y dash 0 is minus 1, so minus of y dash 0 becomes plus 1, and 2sy minus 2sy minus into minus plus 2y0. y0 is 2, so 2 into 2, 4 plus capital Y equal to s minus 1. In this step to this step, I have not done anything except to substitute the values of y0 and y dash 0. Now I know everything here except capital Y. So I'll take, I want to find small y, and I know the relation between capital Y and S. So what I will do is I'll solve for capital Y. I'm doing it steps slowly so that all of you understand. If it's boring, just fast forward it and you go to the solution. So here I have collected y term. Y term comes from s square minus 2s and 1 here, 1 just y. So s square minus 2s plus 1y, s square y minus 2sy plus y. Again, I have written that as s square minus 2s plus 1 times y, and minus 2s I written as it is, and then I'll get 1 plus 4, which is 5. So I written this left hand side as it is just by rearranging and collecting the like terms in the term powers of y, no powers y. And the right hand side I don't touch, just 1 by s minus 1. Now observe that, so maybe, so this is what I have written there. S square minus 2s plus 1 times y equal to minus 2s plus 5, not equal to, sorry, s square minus 2s plus 1y minus 2s plus 5 is equal to 1 by s minus 1. That's what I have written here. S square minus 2s plus 1y minus 2s plus 5 equal to 1 by s minus 1. This, I see that this is, I can write it as s minus 1 whole square. And here, you see, this is the kind of manipulation they expect you to do in the examination. There's nothing very deep about it. Basically, you see, what we are trying to do here is write capital Y equal to something. Why do I want to do that? I want to find small y, which means I want to find inverse Laplace of capital Y. So I'm trying to write capital Y in such a way that it's easy to take inverse Laplace. That's all the goal is. Understand? That's the basic point. I want to write capital Y in such a way that it's easy for me to take inverse Laplace transform. For example, in the previous problem, I'll come back to this problem. In the previous problem, you see, I was trying to write, I did not evaluate this s plus 1, see here, capital Y is 1 by s plus 1 into s square plus 1. I did not try to multiply s into s square is s cube, s into s and 1 into s square, etc. I did not try to multiply. I'm not trying to find capital Y. I'm trying to write capital Y in such a way that it's easy for me to take Laplace, inverse Laplace of this capital Y. So for that, you saw only way is partial, quick way is to use partial fractions. Here also I want to do the same thing. I want to write capital Y in such a way that it's easy for me to take inverse Laplace. How do I know what is the easy way? I observe here when I write this statement. I observe here there is a s minus 1. Here, oh, there is a s minus 1 hidden here. S square minus 2s plus 1 is s minus 1 whole square. Nobody will tell you these things in the textbook. They will write down neatly as I have written in my PPT. This is called s minus 1 whole square, and I'll write minus 2s plus 5 as minus 2 into s minus 1 plus 3. Yeah, this is correct, but why did I think of this? Why did I mean, every time in your life you see minus 2s plus 5, will you write it as minus 2 into s minus 1 plus 3? You will not write it. This is correct, because minus 2 into minus 1 is plus 2 plus 2 plus 3 is 5. Correct. But why did I do that? For that, you have to notice, you have to observe that I want to write capital Y in such a way that its inverse Laplace is easy to find. So here there is already s minus 1. Here there is s minus 1 hidden. So I want to extract s minus 1 from this expression. Extract s minus 1 from this expression means write 2s plus 5 in terms of s minus 1, which is what I have done. Now you take this both to this side. So what happens? This is what happens. S minus 1 whole square y is this minus of 2s minus 1 will become plus 2s minus 1 minus 3 plus 1 by s minus 1. Now divide by s minus 1 whole square. Then I'll get capital Y is equal to 2 by s minus 1 minus 3 by s minus 1 square plus 1 by s minus 1 whole cube. Why did I do this? Because this form, if it is there, it's easy for me to find inverse Laplace of this. It's very easy because it is after all 2 by s. I will not bother about s minus 1. It is 2 by s because if I know inverse Laplace of 2 by s, I know inverse Laplace of 2 by s minus 1. Remember one of the formula which we have used. If I know f of s, if I know inverse Laplace of capital F of s, then I know inverse Laplace of capital F of s minus a. All I have to do is multiply by e power a. Multiply what? Inverse Laplace of capital F of s. That's what I have to do. So everywhere if s minus 1 is there, it's very easy. So capital small y is twice. So I'm using linearity of inverse Laplace. I'm going a bit fast here. So inverse Laplace, you take inverse Laplace of what you see here in the last line. So this will be small y is equal to L inverse of capital Y equal to L inverse of this whole thing. That means L inverse of this thing minus L inverse of this thing plus L inverse of this. That's what I have written. Small y of, I should have written y of x here. That's okay. Small y of x is twice L minus 1, that is the Laplace inverse of 1 by s minus 1 minus 3 times Laplace inverse of 1 by s minus 1 square plus Laplace inverse of 1 by s minus 1 whole cube. This is easy for me to find because this is nothing but e power x. Now I am not writing t. Don't ask me why are you not writing t. Isn't inverse Laplace of 1 by s minus 1 e power t? Why are you writing x? I don't care. You can write whatever you want. The given differential equation, you want it in terms independent variable is x. So I want it in terms of x. So I am doing all this drama. And this inverse Laplace of 1 by s minus 1 whole square. Of course, there has to be a 3 because it is 3 by s square. Then I know how, not 3, sorry. 1 by s, sorry. 1 by s square, inverse Laplace is e power x. Is that correct? No, I'm sorry, I'm saying something wrong. 1 by s minus 1 whole square, what is the inverse Laplace? 1 by s square will be t, so it will be x, correct. So this will be x, and where did that e power x come from? It came because instead of s, I have s minus 1. So I have to take out, I had to take out s minus 1. Instead of s minus 1, I'll write s. Laplace inverse of 1 by s minus 1 square. I'll write it as Laplace inverse of 1 by s multiplied by e power x. That's what I have done here. So minus 3 times e power x into x. And here s minus 1 whole cube is there. So I would have preferred it to be 2 by s cube. Then I would have written in its inverse Laplace is x power t square, which is x square. So same e power x will come out because of s minus 1. So I'm sure you have done this kind of thing. So I will not spend too much more time on this. So inverse Laplace of this whole thing is this. That means this is the function. This is y equal to e power x. Y of x is equal to 2 e power x minus 3 e power x x plus half e power x x square. This is the solution. I will not do this now, but I expect you to check that this is indeed the solution of given differential equation, which is this. That means that y of x you differentiate twice, differentiate once, find out d square y by dx square minus 2 dy by dx, and add that same function. Answer, you must get e power x. And also this is easy to check. When x equal to 0, what is the value of y and what is the value of dy by dx? See, when x equal to 0, here when x equal to 0, these two terms become 0 and this will become 1, so it will be 2, which is correct. What about dy by dx? Dy by dx, you have to do it. I will not do it now, it's a bit painful because 2 e power x, its derivative is 2 e power x, and here derivative you have to use product rule, e power x into, anyway, x is 0 is what I want, so this term won't come. So I'll just take this term, differential of this term into this term. So that term won't come. So derivative of this into this term. And here, anyway, both the terms will have x square. So you'll get minus 1. 2 minus 3 minus 1 you will get. So you can check this. I will not bother about that. I'm sure you can differentiate this and put x equal to 0, you will get answer to be equal to minus 1. So the small checkings are required to make sure that you have got the problem correctly in your exam. This is another question. Much time do I have? 7 minutes, so I'm sure I can do this. So this is another differential equation: d square y by dx square plus 9y equal to cos 2x. Y of 0 is 1 and y of pi by 2 is minus 1. This is very similar to what we did just now. There is no difference. This is also second order linear differential equation. Only thing is here you have cos x. Here you had e power x on the right hand side. So maybe this is just to illustrate that you can take right hand side trigonometric functions also choosing this problem. And I want, as usual, because degree of the differential equation is 2, I need two conditions. So y of 0 is 1 and y of pi by 2 is minus 1. So here the problem is, you see, this is why I chose this. See, in this problem at x equal to 0, y and y dash are given. Two conditions, but y and y dash are given. In this problem, y at two different points are given. This is like boundary value problem. This is not really initial value problem. I want y at 0 and pi by 2. I know what they should be. I don't know what is y dash. Even then you can solve using Laplace transform. This is sort of boundary value problem. That means I want to find y satisfying these two conditions. At 0 it must be 1 and at pi by 2 it must be minus 1. I don't know anything about y dash here. But without y dash I cannot solve this problem, because when I take Laplace transform of this, I'll get L of y double dash will be L of y minus s square f of 0, that is y of 0, minus f dash 0, that means y dash 0. So I need to know y dash 0. I don't know here, its condition is not given. But don't worry, if you tell me y of 0 and y of pi by 2, I can't find y dash 0, but that's equivalent to giving two conditions. How to do that is what this problem is going to explore. Let's assume y dash 0 is 8. I don't know its value. It's not given in this problem. But still, without that I cannot proceed. So I'll just assume y dash 0 is 8 and let us proceed. So taking Laplace of this given ODE, I'll get, this is the given ordinary differential equation, second order linear differential equation with constant coefficients. I get L of y double dash plus 9 times L of y is equal to L of cos 2x. So this I use the formula which says L of y double dash is s square y minus sy0 minus y dash 0 plus 9 times y is log Laplace of cos 2x is s by x square plus 2 square, which is 4. That's okay. Now I'll substitute. I know y of 0 is 1. So I'll substitute that. Y dash 0 I don't know. It is some value, some constant. So I'll take it to be 8. So I'll rewrite this s square plus 9 s square I'll get from here, s square y, and here is a 9y. So s square plus 9 times y minus y of 0 is 1. So I'll get a s term here. Y dash 0 I don't know. I'm calling it a. And the right hand side remains s by s square plus 4. This is nothing but capital Y. Again, I'll use the same methods usual. I want to write it in a way where I can find inverse Laplace easily. Still, I don't know A. Don't worry about it. Just go through. I want to write it in a way in which I can find inverse Laplace easily. Again, I observe this is s square plus 9. This is s square plus 4. And there's a s by s square plus 4. I can find inverse Laplace easily. And similarly, a by s square plus 9, when I take this that side, I can find Laplace inverse of this. I can find Laplace inverse of this also. Of course, inverse Laplace of this will be in terms of a, but that's okay. I will leave it. Let me. I hope it's clear what I have done here. Just divided by s square plus 9 and taken s minus s minus a to this side, so it will become s plus s and plus a, and then divide by s square plus 9. That's what I have done here. Is there some problem here? I seem to have written this is 4 by 5 s by s square plus 9. There must be a multiplication sign here. Oh yeah, there is a multiplication sign. I have written in the next step. I have written it as partial fractions also. This part I know how to write partial fractions. I have not written the details here. Yeah, I written it as a partial fraction. So when I take s square plus 9 below here, I'll get s by s square plus 9 into s square plus 4. So I know how to write s by s square plus 9 into s square plus 4 as partial fractions. That's what I have done here. I have not, means I have done it, but I have not written down the details here. So you please do that part. You know how to find partial fraction. So you take Laplace inverse of this, you will get a by 3 sine 3x, 1 by 5 cos 2x, 4 by 5 cos 3x. How did I get this? So remember, Laplace inverse of this is, if you take 1 by a outside, I'll get Laplace inverse of 1 by s square plus 9, which is sine 3t. Instead of t, I'll use x because x is the independent variable. So sine 3x plus 1 by 5, this is what? S by s square plus 4 would be cos of 2t, 2x. And this is s by s square plus 9 cos of 3x. Okay, that's what I have done. Correct. So a by 3 sine 3x plus 1 by 5 cos 2x plus 4 by 5 sine 3 cos 3x. What do I do with this? What is it that I don't know here? I still don't know a. But I have not used the other condition which they have given me. Y of pi by 2 is 1. That means when I put x equal to pi by 2, I must get this whole term must be equal to minus 1. So that's an equation in A, simple equation in A. I am solving that. If x equal to pi by 2 and gets substitute x equal to pi by 2, then pi by 2 x is, yeah, x is pi by 2, y of pi by 2 is minus 1. So you put x equal to pi by 2 here. So sine 3 pi by 2 is minus 1, and cos cos 3 pi cos 2 pi by 2 is cos pi will be minus 1. Correct? X equal to pi by 2, cos pi is minus 1. Cos of 3 pi by 2 is 0. So this term will go away. So you write down and you will get a is equal to 4 by 5. You do this simple. This whole thing is equal to minus 1. Putting x equal to pi by 2, y of pi by 2 is minus 1. You solve for a, you will get 4 by 5. So then you substitute this here. So you get the full equation. The point I want to emphasize here is you need two conditions to give you the final solution. Two conditions may be y and y dash or y at two different points. Y at two different points is a boundary value problem. Y and y dash given initially means it is, at one point means it's the initial value problem. That doesn't matter. Names are not very important here. Whether IVP or BVP, both you can solve using Laplace transform. How much time do I have? Was past my time. So this I'll do it in the next class, probably the last class. And also I give you some general motivations regarding Laplace transform and its users and some web resources for studying this one. I'll stop my lecture now.